So, last time we managed to render this beautiful blue triangle using the shader object extension API. But so far everything is hard-coded in the shaders, right? The positions in the vertex shader and the color in the fragment shader here. And this is of course not how renderers are supposed to work. We want to pass the data to the shaders from the CPU side. So how do we do that? Well, that's kinda the main design concern of any renderer. And Vulkan provides a number of different options, and there is no right or wrong one really. It depends again on what are you trying to build. Now, I do have some basic idea for what I want to ultimately build in this series, but let's start simple. And the simplest thing you can do in Vulkan is just to send some data with the commands in the command buffer. So basically here, together with the command draw, we can send some data. This mechanism is called push constant. So basically you record this cmd push constant command and just pass some values to it. Now, how much data can you pass? Well, not a lot actually. The spec only guarantees 128 bytes, so like 2 4x4 matrices. And you can query the actual limit that your physical device provides with this max push constant size field here. And as you can see, newer GPUs support sending 256 bytes. But if you want to be compatible with the older hardware, you can only rely on 128 bytes to be available for the push constants. Now, how do we work with the push constants? Well, there are of course two sides to the task. Handling it in the shader and pushing it from the CPU, right? So let's actually start with the shader, since that's rather trivial. You just define a uniform variable, so basically a global, with a special layout qualifier. For example, let's pass this fragment color as a push constant instead of hard-coding it here. Normally, since the OpenGL days with GLSL, you would specify it something like this, right? Uniform keyword, then the type, then the variable name, right? However, in Vulkan, even if we just want to push a single value like this here, push constants are required to be specified as blocks in GLSL. So basically like a structure. So let's wrap that in a structure. Something like this, right? The type name is push, and then it has the single field color. Now, the crucial thing is to specify the proper layout qualifier for this uniform. And thankfully, it's this simple. You just specify push underscore constant as a layout qualifier. Now we can also specify an instance variable name after this closing brace here, if we want our fields to be scoped rather than being global. So let's maybe do that. Basically, we introduce a variable that will hold our structure with a color field using this name, right? Lowercase push. So now let's just replace our RGB values with this vec3 that we have here. And that's it for the shader side. Very simple. Now, on the Vulkan API part, it is of course much more involved. The basic idea is that you just use this cmd push constants procedure. However, if we take a look at its signature, we can see that it takes quite some arguments, including this pipeline layout one, which is another Vulkan object that we have to create in advance. And you might ask, but aren't we using shader objects instead of pipelines? Do we actually need some pipeline layout? Well, it turns out we do. The constant pushing command works with both shader objects and pipelines, and it was created before shader objects even existed, and it needs to know the pipeline layout for which to push the values. So what is a pipeline layout exactly? Well, basically it's a Vulkan object that contains the information about what resources are accessed by the shaders and the pipeline. And resources being your textures, your samplers, buffers, and the push constants. And since it's a Vulkan object, we need to properly create and destroy it. So let's do that. First, let's add a new field to our globals, just next to the shaders, like this, pipeline layout of type vk pipeline layout. It might make sense to consider grouping shader objects and pipeline layout together in some structure, but let's think about this when we have some actual use cases. And yeah, since the pipeline layout and the shaders are related and are kind of forming the pipeline conceptually, I think it makes sense to create it together with the shaders in our create shaders procedure here, right? Maybe we should rename it to something like create pipeline, actually, but oh well. So let's go into our procedure. And even before creating the shaders, let's write the pipeline layout creation code. So here there's a normal Vulkan pattern, right? We have a create procedure that takes the device, the pipeline layout creation info, the allocation callbacks, nil, and where to store the result. Just like this. Let's wrap it in VK check, and let's define the create info structure. Just like this. Now let's take a look at the fields in the structure. So what do we have here? For flags, there is nothing interesting so far, just some extension one. And then there are two arrays, the descriptor set array and the push constant range array. The descriptor sets is something that we are gonna cover later, and those are actually about binding images and buffers and samples to the shaders, but for now we are interested in this push constants. So why is this an array? Given that with the push constants you can only pass a small number of bytes to the shader anyway. So let's see, the push constant range structure here defines shader stages bit set, this one, right? And then the offset and the size, which means that you basically can split even the small push constant data further into parts and set up exactly which regions are available in which shader stages. For example, you could reserve half of the size for the vertex shader, a quarter for the fragment shader, and leave the rest unused. And then the driver can potentially leverage that information to do things more optimal with regard to filling registers and caches and whatnot. So that's good to know, but for our simple program here, let's just have the full 128 bytes available in both shaders. So let's have a slice of push constant ranges anyway, in case we change our minds later, like this. Let's add a single element here. For the stage flags, let's specify both vertex and fragment, like this. The offset can be left at 0, and the size is 128, because this is the maximum size that is actually guaranteed by the spec. Now let's pass that to the pipeline layout create info. Using the standard pattern, count is just a useID2 of len of the slice, and the pointer to the data is just the raw data of the slice, right? Nothing new here. And before I forget, let's actually add a deletion call as well in the destroy shaders here, right? Let's do the usual Vulkan destroy. So destroy pipeline layout procedure, pass the device, pass our pipeline layout, and the nil for allocators, right? Now, funnily enough, this pipeline layout object is sufficient for actually recording the cmd push constants command. However, the pipeline that we are creating, in this case with the shader objects, must also know about the pipeline layout. So if we take a look at the classical Vulkan graphics pipelines that we are not using, you can see that you can pass the layout here, right? And this would be the layout that we have just created if we were using classic Vulkan pipelines. However, if we take a look at the shader create info ext that we are actually using to create our shader objects, we don't pass the pipeline layout here, but instead it duplicates these two arrays that we would pass to the pipeline layout create info. And we need to pass that instead of the layout to the shader create info. And we also need to pass the same exact information to all the shaders that we are creating in a single create shader cxt call. So yeah, this is a little bit awkward of the API. I mentioned already that I kind of find the shader object API a bit awkward in details, but it's fine. Let's just copy paste the push constant ranges array. Thankfully, it's exactly the same fields. So we paste it here for the vertex shader and here for the fragment shader. And that should be actually enough. Now we can go back to our render function to where we have this cmd push constant call and start filling it with actual parameters. And by the way, if we comment out the call here and try to run the application, the validation layer will point out the fact that the shader in the fragment stage uses a push constant, but the cmd push constants were not called yet, so we are covered here. So let's see, the command buffer is of course our cmd, the layout is the one that we just created, gpipeline layout, right? Then we specify for which stage flags, which region do we want to push, right? And since we have just one region, we specify the same stage flags, so vertex and fragment, the offset of 0. Now for the size, we actually need to specify the size of the actual value that we are gonna pass. And what is the actual value? Well, our shader defines the push structure as just a single field of 3 floats, right? A vec3 of color. So what we can do is simply duplicate the structure in Odin and use it to push the push constant values. So let's quickly do it. Something like this, right? In Odin that would be a simple struct with a single field color of 3 float 32s. We should probably define a vector3 type as well, but let's do this later. Now let's actually have a variable of that type, like this, with some actual color, like this. Let's maybe use green this time. And now for the size we can simply use the built-in sizeOf procedure, like this, and the values is simply the pointer to our variable with the push data, just like this. Let's see if that works. And yes, it does. We can now see a beautiful green triangle. If we close the application, there are no errors. So this is correct. Now, push constants in Vulkan is a pretty powerful thing, even despite the limited size, because you can still pass, for example, your projection matrix or something like that changes very often, like every frame or something. And you don't have to manage the memory for this data, right? You don't have to create any descriptors or buffers or whatnot. So this is a pretty powerful concept. Of course, for something like a color, you would probably use buffers or even textures. So this is just an example. But we will make other uses of push constants in the future. So stay tuned.